Hello everyone. This is the video lecture for Calculus 2, section 7.8, improper integrals. They're improper. I have a little note here. It's funny. Some integrals shouldn't go to the ballroom dance. They're improper. They have no etiquette. Yeah, I thought it was funny. Okay, so imagine an integral that says go from 0 to infinity of 1 over x dx, go. So we've got issues, we got problems here. If I integrate this, ln, whatever, even then, just think of like what they're asking about. We have this 1 over x, and we're going from 0 out to infinity, and we need to find the area underneath the curve. Well, notice that this thing will keep going forever, okay? And this thing will keep going forever, okay? And I'm supposed to add up all of this area in here and figure out what that area is. Yeah. So there is a way to do it numerically, I guess, or possibly there isn't a way to do it at all. So we're going to get two different answers a lot of times. Converge means that we can get a real answer, and then we also have diverge, which basically means we get an infinity answer. Okay, so or you just can't find it or something like that. So in this particular case, I believe the answer is diverge. But there are very similar situations, and they say, hey, go and figure it out. And there actually is an answer. If there is an answer, you would say converge, and you would actually give the numeric answer. So how do we even do all this stuff? Well, let's just get started and jump into the first question. They're actually pretty simple. It's just a concept. We have to kind of get used to this concept. I don't know what that was. Okay, so I got negative infinity to 0 of 1 over 2 minus 3x dx. Kind of simple-ish. And it says if it diverges, type diverges. If it converges, then give the number. Just kind of like I was saying earlier, okay? So you might have a possibility of actually typing diverges into the box. And if it works, cool. If it doesn't, then we actually have to go and do the math. I don't recommend that for a quiz, obviously, or an exam. But you either will get diverge or you'll get a number. So let's go and do the math here and figure out what's going on. This will end up with an ln, but to do the steps slowly, we got u substitution is going to be the bottom. Du is negative 3 dx, and dx is now du over negative 3. I'm going to plug in what I got. Remember that this is x equals negative infinity. X equals 0, right? Those are not u's, those are x's. Of 1 over u, and then I have this du over negative 3. The negative 3 can come out to the front, actually negative 1/3. And then I got my 1 over u du, which, like I said earlier, turns into an ln. And then we have to actually find, I guess the answer is the integral here. Let's convert back into x's. And so then that was a 2 minus 3x. Again, from negative infinity to 0. Okay, now hold on. I'm going to have a lot of moments here as I go through where I have to pause and talk about something because I'm not doing something right, or I'm doing something a little different, or who knows what. And in this case, I'm not doing something right. Not that I'm wrong. I'm not going to say I'm wrong here. I'm just not doing it properly. Improper integrals, that's what we're talking about here. So I'm more of a I guess an improper kind of guy, just in a different sense, where I'm not formal, let's say. What I should be doing is the limit as t approaches negative infinity of negative 1/3 ln of 2 minus 3x from t to 0. That's what I should be doing. Notice that I'm using a limit here. This is correct. This is... I'm not going to say it's incorrect. I'm just going to say it's not really proper. Regardless, in the end, I'm just going to use this, by the way. I'm just going to plug it in. That's what we do here, right? We plug in those limits to find out what we get. So again, this is me. This is not every other professor. This is not even your co-students and all that kind of stuff. This is just me. This is what I do. And a lot of times it works. Sometimes it doesn't. Oh, I mixed up my order. Hold on. Isn't it 0 first and then negative infinity? Sorry. That was just, I shouldn't have been talking. I should just do math. No talking. 0, negative infinity. Okay, so let's just analyze this. I want to just analyze this here and see what's going on. I got negative 1/3 ln of 2, right? 2 negatives made a positive, by the way, there. Ln, and here I got 2 negatives make a positive, so we got positive infinity in the end. Now, again, hold up. Let's just talk for a second. How did I make all this turn into a positive infinity? Well, I've got 3 times infinity. So what's 3 infinity? Let's just do this as a concept, as an idea. I have $1 billion, and then someone says, you know what, I'm going to triple your money. Now you have $3 billion. And, I mean, between you and me, because I don't think you have $1 billion, I certainly don't. Yeah, that doesn't really change my life. If I had $1 billion and I have now 2 more $1 billion, there's not really a lot else that I can do for myself. I already have the cool car. I already have the big house. So now I have even more money. I don't know. I could just shrug. In a way here, I'm saying that 3 times infinity is still just infinity. It's a really big number, and I can't really fathom what else to do with it. And so then I have this 2 right here. So I'm now saying, 3 infinity plus 2. So, okay, cool. We walk up to Bill Gates, and he's like, oh, man, I got $3 billion. And you say, yeah, cool, man. Here, let me give you $2 extra. And Bill Gates just like, what's going on here, man? So, pop culture reference, he's a really rich guy. Moving on, $2 is not going to affect his life. He still has infinity. So, in the way here, what I'm doing is reducing all this down to it's just a really big number. It's a concept, okay? So let's continue working here. This 1/3 ln of 2, that's a number. It's a constant. I don't really know what that constant is, but, let's keep going. Well, I got ln of infinity. So I know it's reducing it in size a little bit, I guess you could say. You had $1 billion. ln of a billion is not a billion. It's going to be in the millions. But it's still, that's super huge, and it's still going to keep going towards infinity. I guess you could say the limit of ln of x as x goes to infinity is infinity. So there's the proper stuff there. Basically, this thing here turned into an infinity as well. So now I've got a constant number. I don't know, I'm going to make up something that -4. There you go, -4. Totally not -4, but it's just a number, and I'm going to say plus infinity. Well, guess what? We got infinity. And if I got an infinity answer, the thing you're going to type in the answer box is diverges. Diverges. And so that is the answer for this one. And then you move on. You're done. So I have another note here. It says, I don't use limits, but in reality, it's just not. I am. In reality, I am. I'm just not doing it properly. Notice I had the little limit here on the side. I am doing limits. It's just that I'm not always explicitly stating them. And I think that we can rationalize this stuff without always having to write it down so properly. Again, this is improper integrals. So you'll continue to see me do this strangeness, and that's okay. You're just going to, that's what it is, okay? If you don't like it, then I'm sure there's another video out there somewhere. But this is how I work it, and I think it's pretty cool, and it's very quick, and it makes conceptual sense. Okay. They say, go and figure this thing out. Again, you have the answer diverges, or you have to type in a number. And I know that a lot of y'all are immediately typing diverges and seeing if it works. And if it doesn't, then you'll go and have to do the answer, Yeah, I know. Again, that's not a good strategy for quizzes and exams. So let's try to focus on how to get this correct the first time. So I'm going to do a U substitution. I noticed that the top power here we can reduce this down like this. There we go. And so I can plug these guys in right here. Again, remember that this is x equals negative infinity, x equals positive infinity. This is not a u. I don't want to mix them up. We'll come back and fix all that here in a little bit. So the x's are going to cancel, and I'm going to have a 3 halves, a negative 3 halves come to the front. And so I have e to the u du. Well, that's an easy integral. It's just e to the u. Again, that looks like a 4. That's why I keep redoing it. Again, it's x equals infinity, x equals infinity, that kind of stuff. So I need to convert it back to x's. So this will be a negative x squared. Now, again, negative infinity to positive infinity. I'm going to do that, I guess, improper way of doing it. And so I'm going to plug in my infinity. 2 negatives make a positive. And then I'm going to plug in my negative infinity. And then I want to know what the answer is. So, let's start over here. I've got infinity squared. So, again, we're going to like $1 billion. You have $1 billion. It's so awesome. And then they square it. Now, squaring something is multiplying it by itself, okay? Like, if you had 100 and you square it, it's 100 times 100. So now that's, what, 4 different zeros. And so we're talking, I think it's 10,000, okay? So we're not just talking 1,000, we're talking 10,000. And that's just 100. Now we're talking $1 billion. So we're talking $1 billion, and now you're squaring it. Yeah, it's enormous. You basically have all the money in the whole entire world. That's infinity. That's infinity. Again, it's just unimaginably large. Over here is a little interesting because notice we got negative infinity squared. I know there's another negative on the outside, but we can't deal with that yet. It's squaring this inside stuff to get a positive. And 2 negatives make a positive. And then still, again, it's a infinity there. What's really weird about this particular problem is that this and this are the same thing, but I got a negative and positive, and so they add each other and make it 0. Not quite. The answer actually ends up being a 0, but not because of that reason. We should look at each of these individually and understand why we're getting a 0. So here we go. E to the negative infinity. Let me graph what e to the x looks like for you. This is e to the x, okay? And that's cool. I like that. Well, as we're going towards positive infinity, yeah, it's going to be like super huge. But that's not where we're going. We're going negative infinity. We're going over here. What is the y value? What's the height as I keep going this way? What's my limit as I keep going this way? It's 0. Essentially, that thing turns into a 0 right there. Same thing on this side. So 0 plus 0 is equal to a 0. They don't cancel each other out. They were both zeros to begin with. You're basically saying 0 plus 0. Did these zeros cancel each other out to make a 0? Well, I mean, no. Yes? Anyways, the idea, though, is that it wasn't canceling. It was the values themselves were zeros. If they're going to ask, and I don't really remember if they ask or not, the answer is converges, obviously. If you get a number, it's converges. If you don't get a number, that is like infinity, then it would be diverges, okay? 78022. I got integral from 1 to infinity of e to the, hold on, make that a little bit better, e to the negative 1 over x, all over x squared dx. Okay, awesome. Figure this thing out, converge, diverge, etc. I am going to use a u substitution, and I'm going to use this power here, I guess, as my u, to rewrite it to make it a little bit easier to actually perform derivatives. I'm going to make it a negative power, so for a derivative, I bring down the power and I minus 1 from it. And so that's going to be a positive now in the front. dx, I'm going to replace my dx equals du. It's divided by now an x to the negative 2, but what's going on in reality here is because that's a negative down here, that's actually going to be a positive like that. Oh, hold on, that's a du. Okay, so it's actually a positive in the numerator. So this is what I'm going to plug in. This is what I'm going to plug in. And so now I've got integral of, again, x equals 1 to x equals infinity. E to the u all over x squared, and then I'm multiplying it by x squared du. These guys cancel, and again, I've got a very simple integral, which is good. We like simple integrals. And so then I actually take the integral. My equal signs don't look very well today. And again, those are x values, so I need to replace everything back into x's. And to do that, I just plug that in right there. This is e to the negative 1 over x from 1 to infinity. How I go about doing this is just the same as all the others. I'm always having to look at my notes, though, because I got these little funny notes that we have to talk about things. This one's not one of those. I'm going to plug it in and see what happens. So I got a negative 1 over infinity, and then minus an e to the 1 over 1. So let's analyze each one of these separately. Notice that I have 1 over infinity. What's going on, and this is calculus stuff, 1 over infinity is actually equal to 0. That's what's going on here. I got it 1 divided by a super huge number, makes basically a really tiny number, and therefore it's 0, goes to 0. So I can replace that immediately with a 0, and then 1 over 1 is a 1. Well, e to the 0 is just a 1, and then I got e to the 1, and actually it's negative 1, I'm sorry. You see that right there? It's negative. That's negative. My bad. I was looking at my answer like, how did I get a fraction? And that's how I got the fraction. It's negative, so you put it in the bottom. Cool. That's it. The end. Done. Super easy. Next problem, 78023. So I've got integral 0 to infinity of 3 sine squared of, is that an alpha? I think it might be an alpha. I think, because, I mean, my handwriting is not the best. I think it might be an alpha d alpha. I don't know, guys. The answer won't have an alpha in the end, so I'm just going to use an x, okay? I don't know what was going on there. I'm pretty sure it has an alpha, so just watch out for those sillinesses. You don't need to do that. All right, so we need to find out what's going on here. There's definitely a couple ways we can go about integrating this. One of them is a formula. I mean, we talked about the formulas. Maybe you have that written down, maybe not. Who knows? If not, though, how are we going to solve this thing? This actually has a formula. It's like power reducing, I believe is what it's called, power reducing. So x equals 0, x equals infinity, and so then I move the 3 out, by the way. My sine squared ends up being 1 minus cosine 2x all over 2 dx. Now, I wrote mine with a 2 kind of in the front just to save a little bit of space. Ultimately, though, that 2 does come to the front, and what we have is integral of 1 dx, still the same 3 halves, and then I've got my cosine of 2x dx. Okay, so when I integrate this one, it's pretty simple. It's just an x. There you go. That's easy. Over here on this side, again, 3 halves, my integral of cosine makes a positive sign. Remember, though, that 2 in the front, I'm going to divide by the 2. So this is going to be a 1 over 2 positive sign. Again, that minus was already there, so I can't change that, of 2x. And now from, why did I put x equals here? I never did a u sub. Whatever. It is x equals. You just then, that was confusing me for a second. X equals, but I never did a u sub, so it was all, yeah, of course it was x equals. Sorry, that was a bit too much there. We should put x equals every time, just to make sure. I'm going to go ahead and plug in these values. So plugging in the infinity here, we got 3 halves times infinity, and I got 3/4 sine of 2 times infinity. And I'm going to plug in the 0. So we get 3 halves times the 0, 3/4 sine of 0. So sine of 0 is 0. 0 times anything is 0, so that goes away. We don't have to worry about it. Cool. That's an infinity. 3/2 times infinity is still infinity. And this is an interesting one. What's sine of infinity? What's sine of infinity? Exactly. So if I look at the sine wave, it looks like this, right? So as I keep going forever and ever this way, what is the height? What is the y value? What is the limit? Where's it going to in the end? You can't give me an answer, because I can't give you an answer. At least not one specific answer. It'll keep oscillating and oscillating. Technically, sine will have a range of 1 to -1. So my answer is somewhere between 1 and -1. Now, it's kind of funny. I've been doing this class for quite a while, and we've used calculators like the TI-89 before. This is way back in the past. And when you type in integrals like this, it gives you weird stuff, weird answers sometimes. And it doesn't give you a plus or minus 1, but it says like sine infinity. It'll just say, hey, sine infinity. And you're, as a calculus student, supposed to understand that it really means it's a plus or minus 1 range, something like that. Regardless, this is what we're looking at here. I don't know what the exact answer here is. It's somewhere between -1 and 1. But this guy's an infinity. So I'm looking around here. I got -1 and 1. Like I'm like, hey, you know, got $1 billion. So I'm going to either take $1 from you or I'm going to give you $1. And you're like, you're wasting my time. I've already got $1 billion. The answer is infinity for this. Therefore, you're going to type diverges. I hope that the concepts that I'm trying to get across here are making sense. I know that my numeric approach is not standard. Certainly, nobody that I know plugs in infinity. They say the limit of blah, blah, blah equals this and that, da, da, da. That's fine. You do that if you really want to. I'm not going to do that. It's too much writing, and the result is the same. I will warn you when there are times when this kind of method is a little on the cheesy side, okay? So I'll warn you, and I'll show you why I would maybe like go back to a limit or do something else, but 90% of the time, this is fine. So I got a z, and I got a z squared plus 4 dz. You guys are now advanced math students, and I'm going to tell you a small story. I used to type 2's and z's, and that was how I wrote my 2's and z's. Can you see how I got something confused once in a while? So as you keep going in math, if you're still doing this, I recommend you start slashing your z's so that you know there's a difference between a 2 and a z. Maybe you do your 2's like this and there's a z. That's fine. I never did my 2's like that. So again, it kind of depends on the person, but this is a small, piece as we keep going. Look, guess what I'm going to have this look like here in a second. This is a perfect example. It's this guy. You see, if I were using the non-slashy z, then I would be way confused here because my z's and 2's look exactly the same. There would be no difference between them. Okay. So watch out for that. I actually messed up this problem a very small amount. I guess I was so excited talking about it. This is actually a 4 right here. But what that does, what I'm going to be doing, is making that a z squared, and this is a 2 squared. I'm always thinking arctangent. In fact, this time it actually is an arctangent, so that's kind of nice. So let's do some math here to make this thing work. I'm going to start with a u substitution being my z squared right here. And so then my du is a 2z dz. And so dz is equal to d... Ooh, I zoomed in. Okay. Du divided by 2z. And so I can replace what I've got. I got a z over u squared plus 2 squared du divided by 2z. The z's are going to cancel. The 1/2 comes to the front. And so, again, this is x, right? No, this is z. Okay, whatever. Z is equal to negative infinity. Z is equal to 0. We're going to have to remind ourselves to come back to actually solve this thing here in just a second because it's no good the way it is. Okay, cool. It is arctangent, by the way. Notice that I have the 1/2 already in the front, but this 2 right here means that I'm going to have an additional 1/2 arctangent of, and then I got my u over 2. U over 2. I think that's, yep, that's it. Cool. So from, again, z is equal to negative infinity to z equals 0. And I'm going to convert that back now. 1/4 arctan of now not u, but z squared all over 2 from negative infinity to 0. I'm going to plug these guys in. And so then I got 0 squared over 2 minus 1/4 arctan of negative infinity all squared. Let me make that a little bit better looking. Negative infinity all squared all over 2. And there you go. All right, cool. So arctan of 0. What is going on here? Well, arctan is saying give me the angle for the slope of 0. So you got a slope of 0. What's the angle? And if you draw it out, my slope of 0 is a flat line, right? So what's the angle right here? Well, it's 0 degrees, or you could say 0 radians. This one's a little different, though. I got 1/4 arctangent of, and notice I got negative infinity squared, so that's going to be 2 negatives, make a positive. Infinity squared, it basically goes to infinity. And then I'm going to say, oh, infinity divided by 2, well, that's still an infinity. So basically I end up with a positive infinity. So what's arctangent of infinity? I draw the graph for this. Arctangent looks something kind of like this here. And it actually limits itself to pi over 2 to negative pi over 2. So notice that as this keeps going this way, it's at a height of pi over 2. That's what its limit is. So I guess you can say the limit as x approaches infinity of arctangent of x is equal to pi over 2. Therefore, this whole thing right here turns into pi over 2. I don't have to write this limit every time. I don't. You understand? I don't have to write it every single time. And so my ultimate answer is negative pi over 8. And so therefore you got a number, didn't you? So you would say converges. Convergence. Convergent. Convergent. Converges. Yeah, whatever. Okay, cool. Next problem. This one's a big one. Oh my goodness. 78033. So I've got integral 0 to infinity of e to the negative square root of y dy is equal to what? Okay. So first off, I want to do some u substitution stuff, and it's not exactly the best. We'll see here. So I got my u. I'm just seeing if I missed something because I don't see anything I missed. So that's okay. Is going to be my I'm going to take a positive square root of y, not the negative. I chose the positive for some reason. I'm just going to stick with that. So this is technically then to the 1/2 power. My du would be a 1/2 y to the negative 1/2 dy. And of course, I want to go ahead and solve. So I'm going to take these and move them over here. That's going to be now multiplied by a 2. That's going to be, as was in the denominator, now it's going to be in the numerator, square root y du. So that's what I'm going to plug in here in just a second. Okay, so I got integral now. Again, y equals 0. Y equals infinity. Of, and I've got e to the negative u, and then my dy turned into a 2 square root of y du. Now that's kind of weird because I thought we were going to get rid of all our y's. Well, it didn't happen. And that's okay. But you know what's interesting is that this u is equal to the square root. So what I could do is replace that with a u. And so I've got e to the negative u times 2u du. And now we're talking here. Now this is something that we can actually accomplish. Not easily, of course, but it is possible. Notice that the 2 will come out to the front, ue negative u du. I have here in my notes that you can either use a formula or integration by parts. The formula is pretty easy to use. I don't know what that formula is. I didn't do it. But there is a formula. You can use it. I'm going to do integration by parts instead. V is equal to U, because, again, I don't have U and V. I'm going to use a V and a W now, because it's just weird like that, I guess. But, hey, you know what? It's calculus, too. dW. So, again, now this is what I'm going to integrate. And I chose these because I chose these. So, there you go. Integrate this guy. What you're going to do is actually divide by the derivative of the top. And, well, it's just a negative, so it doesn't really change much. Okay, so what I actually got is VW minus integral of W dV. You got that right? So U... it's just integration by parts, just using different letters, because we ran out of letters. And that happens. Notice the two negatives are going to make the positive. And so then I integrate this guy. Well, we just did that a second ago. Just negative in the front. From, again, remember, this was, what was this? Z? Y. Y, 0 to infinity. Y equals 0. Y equals infinity. So I have to replace all my u's with y's. If you remember, that was the square root of y. Whew, here we go. Square root of y. E to the negative square root of y minus e to the negative square root of y from 0 to infinity. You could factor out this e to the negative square root y. Notice that we're going to have a negative 1 right here. And so we got negative square root of y minus the 1 from, again, 0 to infinity. Cool. So at this point, what do? We plug it in. So I'm going to plug in the infinity. I'm going to plug in the 0. Uh-oh. 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 Yeah, this is going to be interesting topic of discussion here, okay? Don't think I'm just letting you go after this, okay? There's a lot more going on. Oh, hold on, that's a 0. Okay. So I plugged in the infinity, plugged in the 0. I have e to the 0. E to the negative infinity. We already talked about that. That was a 0, right? And I know that the square root of infinity is infinity, so we got an infinity there. I don't know. And then e to the 0 is a 1, and then we got 0, and then we got a negative 1. Well, this guy, 0 times n is 0, isn't it? So we got a 0, we got two negatives, we got positive, and so my answer is... Oh, there's a 2 in the front. Hold on. Where's my 2? Where's my 2? Ah, look, I missed it again. So there's like a 2 in the front of all this here. 2 in the front, 2 in the front, a 2 in the front. Ah. You ever do that? I know you do that. And so my answer technically then, of course, here's 2 in the front, is going to be a 2. That's my answer. Yay. And that is correct. That is correct. But we cannot leave it at that. No, no, no. Because I did something wrong. Not wrong, just improper. Ah, right here. Right here. Okay. 0 times anything is 0, right? So 0 times infinity is definitely a 0. Sometimes. Sometimes. Okay? Sometimes it's not. You're thinking, what is going on with this guy? Yeah, I know. We could do strange math all day. You want to see another strange math? This is really funny. So infinity is 1 over 0, isn't it? And so the zeros cancel, we get a 1. Yeah, no, don't. My point is, like, I can make up whatever I want at this point. This was very bad of me. This is bad. Don't do this. This is bad. But I want to discuss why it's bad, and then we got to say why it's what we should be doing instead, and how did we still get the correct answer in the end? You know, there's a lot of questions here that are conceptual, and there's a perfect time to talk about them, okay? So I'm not letting you go. I got a whole page just devoted to this. I have a whole page in my notes just for this, okay? So let me turn to blue. I'm going to do blue here now for all this stuff. Okay, so let's start back with what we had, okay? And I want to talk about the situation one step earlier. I was plugging in the infinities, and I said, that's got to equal 0. That was my conclusion. Well, let's do some analysis here again. So, and this, I'm going to take it slowly here. This is e to the negative infinity, and we already saw this was equal to 0, right? And I saw this guy right here, square root of infinity is definitely infinity. It's still like you got a bazillion dollars, you take a square root of it, you still got a bazillion dollars. I know that it's less, but it's still a lot. And so that's how I'm getting my 0 and infinity stuff. And again, my analysis was, 0 times infinity is 0. But that is incorrect. And we need to talk about why and what else. Okay, so that was what's going on. We recapped. Now I'm going to do something new. This is new. Let's discuss comparison something or other. I think it's called comparison, or I don't know what it's called. Comparison of functions as you go to infinity. So I'm going to write this huge thing out, and then we're going to discuss it. I got ln of x is much less. That's 2 alligators. That means much less. Much less. Let me write that down in case you can't understand my accent, I guess. Much less. Not just less. It's much less. Okay? That's what it means. It's not just a single. It's a double. It's, a whole lot less. So ln of x is much less than the roots. I'm going to put a little n up here if that's okay, to give it a little bit more oomph. Is much less than my linear term, my linear singular term, I guess like a 1 power, is much less than my polynomials. Again, n power just kind of represent that we got polynomials there, is much less than e to the x, or really anything that is exponential, is much less than my factorials. Wow, we haven't seen those in a while, right? Factorials. And then finally, the factorials are much less than x to the x power. Now, I had to go and ask some other professors about what this name is here. And apparently, they call it power tower. Sounds pretty cool. Power tower. Because, and you can keep going. You can put another x up there as well. You can keep on stacking them. And that is weird. I think we actually do have a question or two about that later on in like chapter, I can't remember where, super far from here. We do actually have a question or two about it. So I do include it. But it's such a rarity, at least at this point, that I'm not going to really discuss all the particularities. Okay. So what is all this much less than meaning here? What I'm going with is that as I'm approaching infinity, so I'm approaching... my x is approaching infinity, then what I have here is that this is the smaller, and it's going towards the bigger stuff, okay? I'm going to do a graphical approach to show you, but honestly, between you and me, I never really used the graphical approach in my mind, but I do want to show it. Maybe you like pictures more than me. I don't know. I do like pictures. So this is the graph of ln of x. Let's just stop and talk about it for a second. So is this eventually going to go higher and higher and higher and higher and higher? Will it eventually go to positive infinity? Yes, it does actually keep going up forever. It will go to infinity. It's just kind of slow. Let's just say it's kind of slow. So that's my ln x. My linear term, I'm just going to graph the linear term here. This is just x. And notice, it's going to keep going up forever and ever and ever, right? It's going to go to positive infinity for my y values as well. Cool. But it's faster than ln. Let me do another one. Here we go. This is the e to the x. Notice, it's going up real fast. Yeah? So is that going to infinity? Yup. And it's going there much, much quicker than an x would. Much, much, much quicker than an ln x would, okay? So this is the idea behind it, is that you have your smaller versions, and they're still infinity. It's just that they take a little longer to get there, versus way over here you got your bigger stuff. And so like whenever I say, let's just make a comparison here, I say ln of infinity, and then I have like e to the infinity. What's going on here is that this guy here is smaller, and this dude is bigger because he's further on that line here, okay? He's further on that line. So, yes, the answer here is infinity, and yes, the answer here is infinity, but this infinity is bigger. It's kind of like saying infinity and infinity. And so, like, there's a difference, kind of, in concept. Do you see a numeric difference? No. I could write a 2 and a 2, and that doesn't change anything. You have to see the concept. Infinity is not a number. It's not a number. It is a concept. And so there is, I guess, magnitudes of infinity. There's some infinities that are bigger than others. Okay, so how does this all relate back to what we've been talking about? If we had originally an e to the negative infinity and we had a square root of infinity, these guys were in our problem earlier. Look back right here and right here. And I said, oh yeah, blah, 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 0 or whatever. Well, I mean, yes, it's 0 because it's 1 over e to the infinity. 1 over 0 makes the infinity. See what I'm going with here? I'm sorry. Whoa, I mixed that up a little bit. This is 1 over infinity makes it 0. There we go. So I'm still really focused on the exponential. I'm not really concerned about the negative or positive right now. Let's just focus on the exponential side of things. So this guy here is 1 over e to the infinity. He's 1 over something that's really darn big. Okay? 1 over big infinity. But the square root, if you go back to my list here, the square roots are a little bit further down the smaller side. We're talking exponentials versus this guy right here. This is magnitude smaller than this one. This is big. This is small. And so what I'm saying is what I have here is a tiny little infinity. And so I'm wanting to merge these together, I guess you can say. What I end up having is, notice again, I have this guy and it was times this one here. I had said, oh, well, this is 0, and this is infinity makes it 0, right? Again, that's incorrect. That's not what we're going with here. I want to now analyze this as saying this is a negative power, so it's 1 over something that I can recognize, 1 over a big number, times a small number. So in the end, that small number is in the numerator, and the big number is in the denominator. Now, my answer here, I'm going to say, is 0 now. That's my answer for this concept. But let's give it some numbers to understand what I'm talking about here. Give me a small number. Oh, I don't know, maybe 0001, something like that. We're talking tiny, right? In comparison, we want something big number, okay? Huge, magnitudes bigger than this, okay? I've only got a fraction of a penny, and the dude's got billions of dollars sitting right beside me. That's the difference that we're talking about. That's the magnitude difference that we're talking about. Put this into your calculator. What do you think you're going to get? You're going to end up getting a 0. Now, if you got a really fancy calculator, they'll try really hard to give you all those zeros and then a 1. But yeah, ultimately rounded like 2 decimals. What do you think? 0. And that's how we got the 0. That's how we actually get the concept that this whole right here was a 0 in the end. Not because of this, but because of this bigger and smaller stuff. I will be using this extensively later in this class. This is only a taste of what we're going to do here. But like the last chapter is almost devoted to this stuff. And we're going to be seeing this as a concept again and again throughout the rest of the class, okay? So if it's not 100% right now, don't worry. I will definitely re-explain everything later. But for now, that's where I'm getting my concepts. Okay. Whew. Now I've got to be a good professor for a second, okay? So ultimately, again, I got it. This is the good stuff, okay? That's all. That was all just Chad stuff, okay? This is actually like what other professors should actually teach and stuff like that. So anyways, this is what we got. And I need to find out what is this equal to whenever I have this limit thing. So let me do it more properly. I've got my limit as, say, x goes to infinity of the square root of x over e to the x. Again, negative power means it's in the denominator. And I end up saying, oh, that's infinity over infinity. Does this look familiar to you, Calculus 2 students? Maybe you've seen this in Calculus 1. That's right. It's L'Hopital's. It's not La Hospitals. Don't say La Hospitals. It's L'Hopital. Okay, so L'Hopital. And so how I approach this is I say, L'Hopital's, we now just, continue on. So equals, and I put a little LH to remind myself why I'm doing all this. That's an equal sign, and you can make equal signs really big, and you can tell what you're doing with the step like that. If you remember, L'Hopital's is actually just the derivative of the top and the derivative of the bottom separately, and then you just redo the limit. So my derivative of the square root of x is 1/2 x to the negative 1/2. Cool. The derivative of e to the x is still just a plain old e to the x. Awesome. Well, let me simplify this thing because it's, gunky. So I've got 1 over 2x e to the x, something like that. And now I plug in the infinity. What you're going to get is 2 times infinity, and then e to the infinity, and infinity times infinity is infinity, big infinity, and 1 over infinity is a 0. And that's the proper, the good way to do it. That's the L'Hopital's numeric calculus professory kind of way of doing it, okay? Cool. I will rarely do that, but I will still do it occasionally to show you the I guess the science behind it all, okay? But I really truly stress the concepts here, okay? These concepts about bigger and smaller infinities, very important, and it's very fast. And it's very fast. Okay, finally we can move on to another problem. So here we go. I got -2 to 3 of 2 over x to the 4th dx. It says, before we go, let's, if at all, let's graph it. Oh. Apparently I just got the answer by looking at it. That's cool. Yeah, oh, I know why. Yeah. Okay, so I'm looking at it and I'm having like a math eye, and it diverges. Okay. Yeah. Okay, cool. We're moving on now, right? You could see that. Can you see it? No, of course not. Oh, I mean, maybe you can. I don't know. Let me graph it for you, and I'll show you why. You can just kind of look at it and say, ah, you're funny. So this is an even power, so we're going to have the 2 sides here on the same height. They're wanting the answer, the area from -2 all the way to 3. So they want all this area here, and all this, and all this, and all this, and all this, and all this. And it looks like it's getting pretty close to 0. I mean, do you think maybe it actually ends up being that way? Some problems, you could just say, yeah, it's approaching 0, and it will actually provide a numeric answer, okay? This one does not. This one actually does not. So to me, this area here, this area is infinite area, and so then it diverges, and there you go. But that's not good enough. It's not good enough at all. What we need to do instead is actually integrate this thing. So remember that we had the -2 to 3. Oh, that's a 2 on the top. X to the 4th dx. So what I'm going to have to do is split this thing up to find the total area. You split it up into -2 to 0. And then we're going to go from 0 to the 3. But it's the same thing. So I need to find the area of the first one, area of the second one. We add them up and call it a day. Okay. So this is technically a -4. So to integrate, I'm going to add 1 to the power and divide by the new power. So again, -4. Let me just remind you here. Talking -4. So I'm going to add 1 to this power and divide by the new power. So that's not going to be a -3 over -3 from -2 to 0. And then plus, the same kind of thing here. We got x -3 over -3 from 0 to 3. So whenever I start plugging in a 0 here, I'm going to go into I'm going to get trouble out of this. 0 cubed. Notice I got 1 over 0. And so to me, that screams infinity. Same thing here. I'm going to plug in that 0 eventually, and I'm going to get an infinity. And infinity answers lead me to diverge again. Diverge. Okay. Now, there's a very funny particular part with this, is that you got a negative infinity and a positive infinity. So does negative infinity plus a positive infinity equal 0? No, again, not even close. I think it's actually like that, and maybe I'm wrong about... No, I think it's actually... I can't remember. I didn't actually do this part. But if you have negative infinity and you have a positive infinity, and you add them up, they do not equal 0 because one infinity could be bigger than another, and who knows what's going to happen. I would say this is a scary moment in your life, and back away, turn around, don't drown. We'll talk about that when we see it, okay? Okay, and another problem. This I got 2 problems left. And again, I have a big set of notes for this one in particular, so you know that's a good problem there. So I'm just going to read this to you. I'm not going to write this all down. Use comparison theorem. I think that's what we were doing earlier. To see the convergence or divergence. And I have a little star here that say probably mean something like inequalities from above. So let me restate. I'm gonna show you the question here, and then I'm going to restate my comparison infinity magnitude line thing. I don't have a good name for it. So I got my ln x is much less than my nth root of x, square root, I guess, x. I got regular x, and then I got my x to the n, and then I got my e to the x, and then I've got my x factorial, and then I've got my x to the x. Okay, cool. So that's my line, and I think they're trying to say to use this thing to figure out what the answer is. I guess that's not too bad. How I approach this, and this is just me, and I think this is how they're wanting you to do it. I could be wrong. I first off remove the 36 entirely. So like, okay, 36 times infinity. It's still infinity. So I'm reducing this down. I'm comparing it to this guy right here. And let's just do another quick thing. Let's get rid of the plus 1. Again, I got $1 billion. You add $1, and it doesn't do anything. So, okay, cool. Well, again, this is kind of equal to... Again, I'm just comparing it here with these x's cancel and leaving me with 1 over x squared. Okay, so now we're looking at this guy and saying, hey, does this converge or diverge and all that kind of stuff here. And so let's see here. I've got my integral of 0 to infinity of 1 over x squared dx. If I can find out what's going on here, if it's converge, or diverge at this point, then I should be able to figure out what's going on in the bigger picture of things. So what I have here is a negative power, so he's 1 over something. Let me just real quick integrate this guy so that you can kind of see like what my thoughts are, my theory on this. And so I've got x to the negative 1 over negative 1 from 0 to infinity. This is just real quick stuff here. That's a negative 1 over x from 0 to infinity. If I plug this stuff in, I've got 1 over infinity, and then I've got 2 negatives make a positive, 1 over 0, and so I've got, I basically got 0, a negative 0 plus infinity, and notice again, whoa, is that going to be infinity? Infinity plus 0. Do I get infinity? Hold on. Let's just pause for a minute here, okay? So I'm kind of confused about what's going on here. Okay, let me just make a side note. I have something else I want to talk about, okay? And again, I have this big side note, and then we're going to talk about the rest of the problem. So I'm kind of confused about how to go about this. Let's go do a different thing for a minute, okay? What if instead I had 1 to infinity, okay? What if I had 1 to infinity instead, and I'm trying to figure out what the answer is to this guy, okay? So let's talk about it. If I did my integral, again, negative 1 over x from 1 to infinity, I plug in my infinity, and then I got 2 negatives make a positive, 1 over 1. So basically 0 plus 1 is 1. And I'm not saying the answer is technically a 1 here in this particular case. My answer, I just look at it and say is 1. No, this is converging. This converges. So pause for a second. All of a sudden, I have this diverges if I had it from 0 to infinity. So this guy right here, I'm assuming for just a second, diverges. Okay? But then I look at this guy, and I could definitely, all day long, I could tell you that this guy converges. Okay? For sure. Just because I changed a little number at the bottom. Well, my original still had a 0, so how am I supposed to affect this here? Let me show you what WebAssign does, and I'll show you the what they're doing. Okay, so this is WebAssign for a second here. 0 to 1 of my 36x over x cubed plus 1 dx plus integral from 1 to infinity of my 36x over x cubed plus 1 dx. They're saying that my original can be split up between 0 and 1 to infinity. I just proved to you that the 1 to infinity definitely converges, okay? It gives me a number of some kind, and that's cool. So what about this guy? And here's the part that WebAssign says. WebAssign says that this is a constant, that actually yields a single number, okay? And so I'm just going to say here, and this is converges. This means that we also get a constant number. I don't know what that is. So I got a constant number. I got a constant number plus another constant number. Guess what? You're going to end up with a constant number, and therefore the whole thing will definitely converge. That's your answer. You click converge, and you walk away. Now, on this problem, it has converge or diverge, and you're sitting there like, I don't know, diverge. And it says, yeah, you're wrong, and then you go and click converge. It says, yeah, you're right, and you move on. You never think about it again. Hold on. I mean, yes, that's fine for the homework, but not for quizzes and exams. So we've got to talk about why all this stuff happens. I have a note here. So how, this is on my notes, I put a big how do they know that that was a constant? That was literally their notes. They said, well, that's a constant, so therefore, and they moved on. Let me tell you how. Well, the calculator says so. I'm just reading to you. But how would we normally do it? That's a good question, isn't it? So I went to a calculator, a big-time calculator, and I put that thing in, and it said, blah, 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 it's a number. And cool. So how would I do it without a calculator? Because, again, I'm not thinking calculators here. If we could do this integral, I would have done that first. Apparently this is a bad problem. I literally wrote bad problem at the bottom here. So just, this is why we do these problems here. I don't want to leave you I don't want to leave you. I don't want you to just be confused. So yeah, go back. This problem number right here, 78057. It's just a bad problem, okay? It's not that it's wrong. It's just that it's not really adjusted for what we're doing right now, okay? They suggested use a calculator, and they did this constant thing. It's just a bad problem, okay? It's just a bad problem. 78061. So I've got integral from 1 to infinity. This is actually the last one, of x plus 1 divided by the square root of x to the 4th plus 1 dx. And I'm using the comparison stuff again. This one's actually going a lot more smoothly because there's a 1 right there. So, so let's do the math here. I'm saying this is basically equal to an x divided by the square root of x to the 4th, which is basically equal to x over x squared, which is basically equal to 1 over x. And this right here should trigger, eventually, not right now, should trigger diverges immediately in your mind. Okay? So that's your answer. Diverges, walk away, done. Again, in the future, when you get to the next chapters later down the line, you see this, you say, diverges. It's a P series or whatever they would call it. Because there's a 1 power here, then just automatically it's not going to work. That's cool for later, not right now. How do we do it today? How do I know that this diverges today? And so I'm going to take the integral, and that's going to be an ln of x from 1 to infinity. And so then what I do is ln of infinity minus ln of 1. Make the 1 look a little bit better. Well, ln infinity is infinity, but ln of 1 is a 0. So infinity minus 0 is infinity, and again, I get the diverges answer. Cool. I hope that you're seeing that there's a lot more to this than just plug it in, than just, help me get the answer. There's a big set of concepts here, and they're really cool, and we will use them through the rest of the class. So this is just a taste of what's going to happen. When we get to them again, I'll re-explain, and we're going to have a lot of fun. So that's it. That's all I got. Thank you very much. Have a great day.